Next is atomic radii. If we look at the 3D series first, atomic radii and ion radii of the same charge in a given series show progressive decrease in the radii with the increase in atomic number. It is a general observation we saw here. Here is a radii in picometers. It starts roughly with a 164, 163 picometers for scandium, then start reducing for titanium, vanadium, chromium, manganese, iron. Here almost stagnation. This is almost stagnated, very shallow slope. But in the end of the series after nickel, it starts rising again. We see an increase in atomic radii in the end of series. This is we are talking about 3D series. Now, what could be explanation? Let's check it out. The new electron enters a d orbital. Each time the nuclear charge increases by a unit. We know with the increase in d orbital electrons, the nuclear charge in the core increases too. So here this is true from we started here 3d3, 3d5 chromium. The next we having here iron core, manganese, then iron, manganese core, then iron core. This is up to iron. This is iron core. This is 3d5 4s2 manganese. And similarly, here we have up to from after iron cobalt to zinc. The reason is why we see this phenomenon, because the shielding effect of d electrons is not that effective. Shielding effect means the screening of outermost electrons or the intraorbital electrons from the nuclear charge. This shielding effect of d orbitals electrons is not effective. Hence, the net electrostatic attraction between the nuclear charge in the core of nucleus and the outermost electron increases. As we go down this series, what happens? Because of the increase in nuclear charge, first there is increase in nuclear charge as you go down with increase in atomic number, and with increase in atomic number, the number of electrons, d electron increases. The thing is, these d orbitals do not shield the nuclear charge as effectively as p orbitals do. That is the reason. It means, so these electrons in d orbital that we have added, they experience a greater effective nuclear charge that have increased at the core because of increase in atomic number. Because of greater force of attraction, we saw decrease in atomic radii, because now each electron adds up here in the d orbital. That's what happens. These are the explanations for the decrease in atomic radii first in the d block series. But this is not all. We saw stagnation. Stagnation is because of, now here we have greater number of interelectronic repulsions, because all electrons adds up in these paired orbitals. Increase in atomic radii in each d block series in the end of the series, we can ascribe that to the interelectronic repulsions. That's what we see. That is the reason in the end of the series we saw a slight increase in atomic radii, because here these electrons for copper or zinc has to come in the very crowded atmosphere. You see here we having fully almost filled orbitals, and under these conditions these last electrons will experience greater degree of interelectronic repulsions. That is the reason for the spread. The radii of 5D series are virtually or almost same as those corresponding to the members of 4D series. Here that's what we see. 4D and 5D have almost the same atomic size. Why it is so? It is because of the phenomenon known as Lanthanoid contraction. Since 4f orbital have higher spatial spread, we know f orbitals are more diffused than d, and that is the reason they have a poorest shielding effect. Under the poor shielding of 4f orbitals, 5d orbitals experience a greater nuclear charge. That is, the last 5d series, they experience a greater effective nuclear charge and their size will reduce, and which is almost same as 4d series approximately. This phenomenon is known as Lanthanoid contraction. Four orbitals are lanthanoids. Regular decrease in atomic radii of 5d transition elements is called Lanthanoid contraction. So because of 4f elements, so they are responsible for this similarity in 5d and 4d elements atomic size. That's why the phenomena in general we can say Lanthanoid contraction is responsible for 4d and 5d size similarity. Second and third have greater degree of enthalpy of atomization than element of first series. Same again, the reason is presence of filled 3d orbital in the inner electron configuration for second, and 4f orbitals in third series. Here we are talking about, this is the third series here. The nuclear screening effect of d orbitals electrons is lower than f orbitals. That's the same like Lanthanoid contraction. In 5d series we saw their size is almost similar as 4d. But what happens? Both of these atomization is having larger than 3d. The reason is same Lanthanoid contraction. What happens? Just like we saw in atomic sizes, for 3d orbital which having a poor shielding effect, but 4f orbitals having a still poorest shielding effect. So these elements having a higher atomic number, mean higher nuclear charge, and 4f orbital which are intervening between the outermost valence shell and core, they are not that good to shield the nucleus from outermost electrons. That is the reason these elements in 3, 4d and 5d series experience relatively greater nuclear charge compared to 3d series, which have only 3d inter-electron screening in 3d, which is not that effective, which is having a still better compared to 4d and 5d. So the nuclear force faced by outermost electron is far greater in second and third transition series, mean 4d and 5d, which is a second and third transition series, the 3D elements of first transition series. This is how we'll come to a conclusion that because of presence of 4f electrons in these 5D and presence of these intervening electrons, they having higher enthalpy of atomization compared to 3D series. Now, next phenomena is increase in density. What we saw here, density increases across the series. The reason is decrease in the metallic radius coupled with increase in atomic mass, which results in general increase in the density of these elements across the period. Now, if we see, we know this radii first decreases down the series. In 3D, we are talking about 3D series. Then what happens? Here density increases. We know what is density? Density is mass per unit volume. Here, volume is because of our radii, which is 443 pi r cube. Simply, we can say these radii will determine dense volume. As volume reduces and atomic mass increases because along the series atomic mass increases, so we are getting a larger mass per unit, lower volume. So density will increase down the series simply. Since in the end of the series we know volume will increase slightly, that's why density will reduce slightly in the end of series. Ionization enthalpy. For d block elements, removal of one electron alters the relative energy of 4s and 3d orbitals. So, the unipositive ions have dn configuration with no 4s electrons, got low first ionization enthalpy. Let's check it out. First, we see chromium and copper. We saw for the second ionization enthalpies for chromium and copper are unusually high compared to nickel and vanadium. This is because we know these elements having electronic configuration of 4s1, 3d5 and 3d10 respectively. That is the reason after losing first electron, they find it difficult to lose second electron because they acquired already half-filled and fully filled d orbital stable state. Next, for manganese we saw the first ionization enthalpy is high, and for zinc first ionization enthalpy is high. Here's the same thing because zinc got a and manganese got a half-filled and fully filled electronic configurations. These configurations are stable and not easy to break. That's why the ionization of first electron after breaking this stable electronic configuration causes us greater ionization enthalpy.